Hello everyone, we're in example 9-16 this time, 9-16. There's a whole lot going on this one, so I'm probably going to read the whole problem statement and then go from there. So what it says is a 24-inch long bar with a cross-sectional area of 1 inch squared is subjected to an axial tensile load of 10,000 pounds as shown in figure 9.19. It says compute the stress, strain, and the total elongation if the bar material is steel, aluminum, and titanium. And it says assume the proportional limit for each material to be as follows. Steel for 34,000 psi, aluminum 34,000 psi, and titanium 125,000 psi. Now the proportional limit is a very important factor. Proportional limit is when Hooke's law no longer works. So if our stress goes above that value, we can't use this equation. This only works if below the proportional limit. If we're above it, then we're no longer in the safe zone. We can't use this equation. We have to use some sort of chart at that point. Okay, so now let's draw the picture. So it said we had a 24-inch long bar. And it has a cross-sectional area of 1 inch squared. And there's an applied load of 10,000 pounds. Okay, now remember that just because I see this load twice does not mean there's actually two loads. So the first thing I should probably do before I even get to the different materials is say, hey, what is the stress? Because that will be the same for all materials. The stress doesn't care what material it's made out of. So let's go ahead and do that. So the stress, actually, sorry, I wrote down my problem statement. I am given what I just showed you, and I said, I need to find the strain in delta for steel, aluminum, and titanium. Okay. There we go. Steel, aluminum, and titanium. So the first step is going to be to calculate the stress. Remember that stress is equal to our load over the area. So it'll be equal to 10,000 pounds over the area, which will be 1 inch squared. 1 inch squared, which means it's simply 10,000 psi. Now if we look back at our little thing, it said that the proportional limit was 34,000 psi for aluminum and steel and 125,000 psi, so this checks out. We are in that nice linear region where Hooke's law still applies. So we can use Hooke's law. Everything's good. And now let's find the strain. So our strain is going to be using this equation right here, but we need to rearrange it. So instead what we're going to do is that the strain is equal to the stress divided by the modulus of elasticity, which was given in the problem statement. I didn't read it out because they're very large numbers. So first off, for steel, the strain would be equal to the stress over the modulus of elasticity, which is going to be equal to 10,000 psi over 30 million psi, which is going to be equal to 0.000333. And if we want to, we can go ahead and calculate the elongation for steel. Or we have to remember that strain is equal to the elongation over the original length. And we can rearrange that to get that the elongation is equal to strain times the original length. So we plug all that in and we get 0.000333 times 24, and that's going to come out to be equal to 0.00799 inches. Okay, that's for steel. Let's keep on moving down here and we'll try it for the other ones. Now I'm going to do it for aluminum. So the steps are the exact same, just different numbers. So the stress is equal to the strain right here, is equal to the stress over the modulus elasticity. The only thing that has changed is that the modulus elasticity for aluminum is much lower. It means it's much less stiff, much more flexible than steel. And so what we hit here is that it is 10,000 psi over 10 million psi this time. And so your strain is going to be equal to 0.001. We know that strain is equal to the total elongation over the length. Therefore, the elongation is equal to the strain times the length, which is equal to 0.001 times 24 inches, which will be equal to 0.0240 inches. Okay, so I have my strain now for aluminum. And you can see that it is significantly larger than the strain for, or my elongation for aluminum. You see it's significantly larger than the elongation for steel. It's 3 times as large because it has a modulus elasticity that is 3 times less. So the amount of elongation possible will be proportional to the modulus elasticity. The lower your modulus of elasticity, the higher your elasticity. And that's kind of strange, but the modulus elasticity is also known as the stiffness constant, and so, or the stiffness of your material. So it makes sense that something less stiff would be more flexible and be able to extend further. Okay, last part of this problem is to do it again for titanium. We're going to be masters of these equations after we're done with this. So the strain is equal to the stress over the modulus elasticity, which is going to be equal to, in this case, 10,000 psi over 16,500,000 psi, which is going to be equal to 0.000606. That's inches per inch, feet per feet, where we want it to be. And we further get that the strain is equal to the elongation over the length, or we rewrite that as the elongation is equal to the strain times the length, because the strain is a fraction. So that will be equal to 0.000606 times 24 inches, and that comes out to be 0.01454 inches. A little bit less than half. Kind of close to about half or double as much as the steel elongated, and about 3/4 of what aluminum elongated. Now the big thing for titanium though is that its proportional limit was 125,000 psi, where the other two was 34,000 psi. So it can stretch elastically without plastic deformation for a lot longer. Now I want to help bring your attention to something. You see how there were 2 equations for strain right here. And the neat thing is we can actually connect those together. So I'm going to go ahead and do this. This is in your book as well, and I think it was in the notes. But I want to go ahead and do it in this example form as well. And so what we get is that the elongation over the length is equal to the stress over the modulus of elasticity. And sometimes what you want to do is find the elongation without having to go through the strain. You want to just do it in one step. Well, let me rewrite this again, but this time without writing stress as stress, let's write it as force over area. So elongation over length is equal to the load over the area times modulus elasticity. And then finally, what I get is that the elongation is equal to the load times the length over the modulus elasticity times the area. This is called the Flee equation. In your case, since we use P for load more often, it'll be the plea equation. Remember, plea. My plea is to hopefully pass this class. This is helpful. It gives us the elongation as a function of our load, length, modulus elasticity, and area. without having to do 2 steps. It's just a 1-step equation. So I hope this helps you, and I will see all of you in the next example. Have a good day.